Hello, welcome to today's video on modulus equations, where we're looking at how to solve a modulus equation. Coming into this video, I'm assuming you've already come across some of the modulus chapter by knowing what a modulus sign does, as well as how to draw some graphs of the modulus of something. But before we begin, I would like to acknowledge that there are actually lots of different ways of doing this particular content. I've seen loads of different methods both online and in textbooks, etc. But like almost all teachers, I think my method is best. However, that isn't just an opinion. I do have particular reasons for saying that in this particular context. For instance, the method I'm going to be showing you today is great because it's just using skills we're already meant to have from other chapters and also within the modulus function chapter, which is good because it requires less memory if you're just having to reuse things that we already need to know elsewhere anyway. This method also has easier algebra involved than some of the other methods I've seen, which always makes things a bit more straightforward to do, which is nice. But not only does it do that, it also requires less lines of working than some of those other methods as well. I've always got students coming to me going, oh, I can't be bothered to do that method because it takes effort to do. But guess what? This method sometimes saves you time with how much you have to write out as well. And not only does it do all this, but as a bonus, it also provides a handy, quick way to roughly check your answers, which is great because it means you can then move on from the question once you've done it, feeling fairly confident that you've probably got it right. So that's pretty good, in my opinion. And so to explain what the method is, instead of trying to explain what the method does beforehand, it's easier just to explain it as we go. So here is an example, and then we're going to talk through the steps. The first step is to draw a graph, specifically for the function on the left-hand side of the equal sign first of all. So y equals, in this case, the modulus of 4x plus 3. For some of you might be thinking, oh, drawing a graph, that seems like a lot of effort, but trust me, putting this little bit of extra time in at the beginning saves a lot of effort in the long run, so it is worth it. And so, sketching graphs of modulus functions, as a reminder, it's just like initially sketching a normal graph, but we have a straight line inside that modulus sign, so that would be 4x plus 3 being drawn like it normally would. So that would be a straight line with a positive gradient and a y-intercept of 3. And then the part at which the graph would normally drop below the x-axis, it's going to be reflected in the x-axis. And what I would have mentioned in previous times when I've talked about modulus functions is that when drawing the graph, it helps if you label both bits of the graph. The half that was from the original graph without the modulus sign involved, I'm just going to label with the traditional algebra without that modulus sign. And the bit that got altered, the bit that got reflected in the x-axis effectively, we can label with -1 lots of what was inside the modulus sign. It's worth pointing out that I also forgot to mark on the x-intercept on the graph, which was -3/4, so doing that very quickly. But also after this, the next thing we're going to do is we're going to draw y equals the function that's on the right-hand side of the equals sign. But that means we're going to be drawing a second graph on this same pair of axes. And if you're drawing more than one graph on the same pair of axes, it's important that you make them accurate compared to each other. What does that mean though? Does that mean we should be getting a ruler out and measuring out an entire scale so we can plot everything 100% accurately? Well, no. When I'm saying to plot the graphs so that they're accurate in comparison to each other, I mean that we just have to make sure certain characteristics are clear on the graph. For instance, a graph with a bigger x-intercept should appear further to the right than a graph with a smaller one. And a graph with a bigger y-intercept should be drawn higher up on the graph. And then lastly, if you've got a bigger gradient, then that needs to be appearing more steep. Both if you have it as a bigger positive number, like 4 is bigger than 2, so 4 is a steeper gradient, but also in the negative direction as well. Like for instance, a gradient of -5 should be more steep than a gradient of -2 as well. Cool, so let's apply that idea to our example continuing on. We could then draw the graph of y equals x plus 1, and of course it's got a y-intercept of 1, so as we've already got a y-intercept of 3 on there, we need to make sure the y-intercept of 1 is below that, but of course still being above the x-axis. And then also to have an x-intercept of minus 1, so that's further to the left than the 3/4 we already had on there, but also y equals x plus 1 has a gradient of 1, which is a number less than 4, so it's got a less steep gradient, so our graph needs to appear less steep. So putting that all together, we could draw a line that looks something like this. That's not 100% accurate, but it's accurate in comparison roughly to what else is going on these same pairs of axes. In fact, I'd say it's accurate to itself. The scale is completely off here, but as I said, bigger numbers are appearing as bigger numbers, which is all I need it to be doing for this graph. I'm then going to label this second graph as well, just because for this method it helps if you have as much labeled as possible, because then you have all the information you need on this graph. And the reason that's going to be helpful is it makes the next stage particularly useful, because until now some of you might have been getting a bit impatient because we haven't got on with actually solving the equations, finding x and then just moving on to the next question. But believe me, by putting this time in at the beginning, it then makes the next steps a lot easier to do. So what are we going to do? Well, see, here's the thing. By drawing the graphs like we have, the solutions are going to be occurring where the intersections between the two graphs occur. And then all we've got to do is then choose the relevant bits of algebra that cause each of those intersections and solve those equations. For instance, we can see that this point of intersection occurs when the graph of minus 4x plus 3 intersects with the graph of x plus 1. So guess what? If we want to find that intersection, we just have to set minus 4x plus 3 equal to x plus 1. And we just have to solve that to get that solution. So going ahead and doing that, multiplying out the brackets first of all, moving the x's onto the right hand side, taking away 1 from both sides, means we get x equals minus 4 over 5. But then if we want the second intersection, that's also going to be easy to find, because that is when the graph of 4x plus 3 intersects with the graph of x plus 1. So all we got to do to find that point of intersection is set 4x plus 3 equal to x plus 1, and we can solve. So take away x from both sides gets us 3x, taking away 3 from both sides gets us minus 2, so x equals minus 2/3. But then not only have we found the answers, we can also check our answers so we can feel very confident before we move on that we've got the correct values. Because for instance, that second intersection of x equals minus 2/3, we can see was this second point we circled on the graph. And looking at the x values on the x-axis, we can see that we were expecting this value to lie somewhere between 0 and minus 3/4. And if you know the decimals or you just know your fractions well, you'll know that minus 2/3 is between 0 and minus 3/4, so I feel super confident about that one. And then the other value of x equals minus 4/5 was this intersection over here, which was between minus 1 and minus 3/4 by looking at the values on the x-axis. And what do you know? Minus 4/5 is between those values as well. So these are both the final answers, but I also feel super confident that we got it correct, with only minimal effort for having to do that checking. However, I know what some of you are thinking. You're thinking, can I be lazy and just not draw the graph and jump straight to those equations we're doing, realizing that the modulus equation is split into those two different bits of algebra and solving both combinations equal to whatever's on the other side? Well, no, that's not really a good idea, because actually the whole point of the graph is actually meant to save you time. Because here's the thing, you don't always need to solve both combinations. So if you just always solve both combinations, you're wasting some effort by solving that other equation, as well as then missing out on knowing which one of the two combinations is the one out of the two that you need, because the graph is also helping you check your answers as you go. So let's take a look at a quick example of that so we can illustrate this issue. So going through the initial bit more quickly for drawing the graph, drawing some axes, we've got 2x plus 6, which would look something like this. So it's got a y-intercept of 6, an x-intercept of minus 3, and then it's going to get reflected in the x-axis for the bit that's normally below the x-axis. labeling both of those graphs as well. We've got the 2x plus 6 part over there, and then the modulus bit, or the bit that's been caused by the modulus sign, I should say, the bit that's been reflected. So minus 1, lots of 2x plus 6 in brackets. But then drawing the other graph, again drawing it accurate to itself, as I said. So therefore this is a graph with a bigger y-intercept, but also a bigger, or rather more negative, x-intercept, because it's got an x-intercept of minus 10 over 3, which is minus 3.3 recurring, and that y-intercept of 10. But also it's got a gradient of 3, which is a bigger number than 2, of course, but therefore it means it's more steep. So I need to make sure my graph looks more steep. So doing that, we could have something that looks like this. So therefore, we mark on our intercepts there and there. But crucially, here's the thing. We can see there's only going to be one intersection. And that's not just because we've only drawn a bit of the graph, and if we continue the graph on, there would secretly be another one. Well, no. Because this second graph we drew was more steep, the further to the right on the graph you go, the further apart the two graphs get. So there definitely won't be another intersection in the future. Continuing with the labeling, we know this second graph we drew was 3x plus 10, but then we can see clearly the way we're going to get this intersection is it's when 3x plus 10 intersects with the minus part of the modulus graph. So that's the minus lots of 2x plus 6 that we had, and therefore we just have to solve that. So we can multiply out the brackets, we can move the x's onto one side and the numbers onto the other, and we get the answer x equals minus 16 over 5. And we are already done. We only wanted one solution, we've found that one solution, and the reason I'm mega confident about that is we're expecting a value that's between minus 3 and minus 10 over 3, and minus 16 over 5 is minus 3.2, which is in between those aforementioned numbers. So therefore we feel very confident that this is our correct final answer, but we also saved effort because we only had to solve one equation rather than two. But in case I haven't done enough yet to persuade any of you that this really is the best method for solving these, guess what? This method is also great because it can also be applied to more difficult versions of these questions. Now, it depends on what your exam board is as to whether you are going to get questions as difficult as this, so please do pay attention to what your teacher says about what you do or don't need to know for your particular exam board. But the thing is, the method I have shown you would work on these more difficult questions anyway. So if you just get good at the method we have shown, you can still do questions like this, where there's a modulus on both sides, or questions where there's, for instance, a quadratic inside a modulus sign or something weird like that. It's still the same idea. We can draw a graph. So for instance, let's do this question very quickly to finish the video off. We could start with the graph of the modulus of x plus 5. So that would look like y equals x plus 5 for the bit that's above the x-axis. And then we could draw that. We could label both sides and label the x-intercept. So this side would be x plus 5. The left-hand side would be minus x plus 5. Drawing the graph of y equals the modulus of 2x minus 3, we could have our straight line, more steep than the other one because it's a steeper gradient than modulus of x plus 5. It's got the x-intercept of 3 over 2, and then the other side, making sure it intersects the y-axis below 5 because the y-intercept is only 3 this time. And then we can label both sides of this graph as well, so 2x minus 3 and minus 1 lots of 2x minus 3. How are we going to find the solutions? Well, we can see that one of them occurs when 2x minus 3 is equal to x plus 5. So take away x from both sides, add 3 to both sides, x equals 8 is the first solution, which makes sense because we can see it's to the right, in other words bigger than the number 3 over 2. And then the other solution we're expecting is when x plus 5 meets the graph of minus 2x minus 3. So therefore we've just got to solve that. So I'm going to multiply out the brackets. I'm going to add 2x to both sides, and then I'm going to take away 5 to get minus 2 on the right, which means that x equals minus 2/3, which also makes sense because we're expecting this x value to be between 0 and minus 5 according to the graph. So once again, we've found both solutions, even though this appeared to be a more difficult equation. So boom, that is how you solve modulus equations. Hopefully you found this video useful, and this method is pretty awesome. So I hope you agree and you want to use it as well, maybe to help solve modulus equations. I'll see you in a future video. Goodbye.